Good morning all. This is Dr. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the interfacing of memory with 8086 processor. The slides are prepared by referring the textbook Advanced Microprocessors and Peripherals, authors Burchandi and IARE, publisher Tata Microprocessor. Interface two 16K by 8 EPROMs and two 16K by 8 RAM chips with 8086 processor with suitable address maps. So the given here we are given with two 16K by 8 ROMs and two 16K by 8 RAMs. In total, we are going to have 4 memory chips. The first one will take as a ROM block 1 and this is ROM block 2. The lower one RAM block 1, RAM block 2. So these 4 memory elements we want to interface with 8086 with a suitable address map. Before going to the interfacing, first we will revise a few memory organization concepts. Let us assume each memory chip contains 2 to the power of n number of location. And for accessing each and every memory location, we have to pass the address. If the address is n number, the memory locations which you are going to have are 2 power n memory location. So for each memory chip containing 2 to the power of n memory locations, where n is the number of address lines to the chip. Based upon the address which you are passing here, one of the memory location out of 2 to the power of n location will be selected. Next, the size of each memory location will depends upon what is the data bus size. If I have n number of bits, each location contains m bits, right, where m indicates the number of bits in each memory location it contains. So the memory chip which we are having 2 to the power of n location, with each location with m bits, we can represent as 2 to the power of n cross m bits. If any memory is represented with 2 parameters like a cross b, the first parameter will define the number of memory locations. The second parameter will give the number of bits for each location. Every memory is represented with 2 parameters. The first parameter I am taking as A will represent how many number of memory locations are there in the memory. The second parameter which I am considering as B, that will specify the number of bits which we can accommodate in each and every memory location. So the size you can take as 2 to the power of n into m in this example. Example, let us consider we have 4K cross 4 memory. So that means here the number of memory locations which we are having are 8K. The total number of memory locations are 8K memory location. The size of each memory location is 4 bits. For accessing one of the memory location, we require the address lines which are n in number. So for finding out the number of address lines, we represent the 8K as 2 to the power of n, and that n will specify what are the address lines are required to pass or to access any memory location for read or write permission. So in the given example, the number of memory locations are equivalent to 8k. 8 we can represent as 2 to the power of 3. 1k is equivalent to 2 to the power of 10. That we can write as 2 to the power of a into 2 to the power of b. We can write as 2 to the power of a plus b. So which is equivalent to 2 to the power of 3 plus 10, which will give us 2 to the power of 13. Here, this 13 will specify the number of memory locations are required. So the number of address lines are required are 13. In 8086, we have the address space, which is 20 bit size. Out of these 20 bits, 13 bits we can use for accessing any memory location of this given 8k by 4 RAM. Now coming to the problem, interface two 16k by 8 EPROMs and two 16k by 8 RAMs with 8086. So first we will take the ROM. The given size is 16k. In the problem they are given two ROMs. Each ROM size is 16k. The total memory is equivalent to 16k plus 16k, which is 32k. For accessing one of the memory block out of these two ROM blocks, which is ROM block 1 and ROM block 2, the size of this ROM, it is equivalent to 16k plus 16k, which is 32k. For accessing any memory location of this, we have to find out how many address lines are required. For that, the number of memory locations we will represent as 2 to the power of some factor. So in the given problem, the RAM size for two blocks is equivalent to 32k, where 32 we can write as 2 to the power of 5 and k is equivalent to 2 to the power of 10, which will give us 2 to the power of 15. So this 32k we can write as 2 to the power of 5 into 2 to the power of 10, which is equivalent to 2 to the power of 15. So the number of address lines are required are 15. So out of the address line space from A0 to A19, we will take the lower 15 address lines, that is from A0 to A14, which are 15 address lines are required. The remaining address lines, that is A15 to A19, are not required for accessing this. So those address lines we can use for decoding purpose. Similarly, in the problem, the RAM size, it is given as 16k. As we are considering two RAM blocks, the total size is 16k plus 16k, which is equivalent to 32k. The memory size is 32k. This 32k we can write as 2 to the power of 5 into 2 to the power of 10, which is equivalent to 2 to the power of 15. The number of address lines are required are 15, that is A0 to A14. Now, out of these address lines from A0 to A19, we are taking A0 to A14 for accessing the ROM blocks as well as RAM blocks. As these two are same in size, the number of address lines are required are same. So if it is provided with any address between A0 to A14, that may access or it may access any one of the memory location of ROM or RAM, because the address will exist for both the blocks. For differentiating this, we will add one more bit. If it is 1, we will access as ROM. If it is 0, it is ROM. Now we will see the address space, how we have to calculate and what is the total memory is required and address space of each ROM block as well as RAM blocks. The total address space of 8086 processor is 19 A0 to A19, that is 20 address lines. For accessing any memory of two blocks of ROM, that is 16k plus 16k, that is 32k, we require 15 address lines, which is A14 to A0. Now we will take A0 to A14. This is the address space which we require. For this, we are going to write each and every bit with the possible combination. So if I have two bits A1, A0, the possible combination I can write is 00, 01, 10, 11. The least value by providing each and every bit is equivalent to 0. The maximum value we will get by providing each and every bit is equivalent to 1. By assigning the address, the range we can give for ROM location for the 15 address lines is 0000 like this, A14 to A0, 111 like each bit for each bit from A14 to A0. This is the address space required for accessing any 32K locations. Similarly for RAM, as the number of address lines are required is 15, from A0 to A14, we are going to use this address space by providing each and every bit as 0 as the least address, and by providing each and every bit as 1 for accessing the higher memory address. By combining the RAM address space and ROM address space, this is the structure we will get. From A0 to A14, for each and every bit is 0 and each and every bit is 1, and assume this one is for accessing any block of ROM, and this address space is for accessing any block of RAM. Now, if we observe the address whichever we are providing on these lines, it is exist both in ROM blocks as well as RAM blocks. So for differentiating either it is ROM or RAM, we are going to take one bit for specifying either that address is, we need one bit for specifying that address is corresponding to ROM or RAM. So till A0 to A14, we can't access any bit. Apart from A14, the left out pins are A15 to A19. Out of A15 to A19, we will select one line. So for consecutive bits, we will select A15. It is not mandatory to take A15. Any bits we can select from A15 to A19. I am taking one bit, that is A15. So whenever I provide A15 as 1, this address we will assign for ROM. Whenever A15 is equivalent to 0, this address is assigned for RAM block. From A0 to A14, it is common configuration for both ROM and RAM. For differentiating either it is ROM or RAM, we need additional bit. That additional bit we are selecting as A15. Whenever A15 is 1, it is corresponding to a ROM location. When A15 is equivalent to 0, it is for RAM selection. Now the address which is generated, we can see here by representing in the hexadecimal by combining 4 bits. By combining 4 bits, these 4 bits gives us 8. The next are 4 zeros, 0, 0. The last one is 1111 F, 1111 F, 1111 F, 1111 F. So in the hexadecimal, we are writing the representation. So from the location 8000 to FFFF, it is corresponding to ROM. From the addresses 0000 to 7FF, it is for RAM. These are the minimum number of address lines are required. The remaining address, that is A16 to A19, we can go for writing any bit configuration. They are don't cares. So for each and every bit of A16, A17, A18, A19, we can pass each bit as zeros or 1. So in total, as it is a 4 bit, 2 to the power of, that is 16 combinations we can generate. Either you can assign all the bits as 0 or 0001 or 0010 like this 1111. Total 16 combinations we are going to get. However, from A16 to A19, that is user size, you can select anything. So the address lines from A16 to A19 are used for decoding purpose, for enabling memory chips along with A15. But for 8086 processor, after reset or power on, the CS and IP register are initialized to the address FFFF0H. Whenever the reset is done or power on the system of 8086, the CS and IP will generate the address, or it is initialized to FFFF0H. So as the programs which are going to be run and initial programs that will be stored in ROM block, so we are going to select the FFFF0H. Should be lies for EPROM. So this address must be lies in EPROM. As we observe, the upper bits are having FFF, indicates all the bits are 1. So for assigning this address for ROM, we will select the A16 to A19 by writing each and every bit is equivalent to 1. That is A16 is equivalent to 1, A17 is equivalent to 1, A18 is equivalent to 1, and A19 is equivalent to 1. So by writing this, the first two, these are corresponding to, till this point, these are corresponding to ROM address space, and the next block is corresponding to RAM address space. Till now we have done till A15. How about A16 to A19? As we said, FF0H we want to assign for ROM block. So we will select the upper bits as 1 for ROM. How about RAM is, the RAM you can go for any combination of the 16 cases, 0002 to 1111. These 16 combinations we can select. For giving consecutive memory location, for increasing the speed of access, it is always better choice for giving consecutive memory location. Here also we will select all the bits as 1. Now, the address generated by combining 4 bits will get as F10008, 0000, 0000, hexadecimal 0, 0000, binary. In the hexadecimal it is 0. So the address we are representing in hexadecimal format. In the hexadecimal format, 4 groups, 4 bits we can combine as 1 hexadigit. Next, 1111, that is F1111, 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 again it is F. So the address space for ROM is F8000 to FFFFH. Coming to RAM block, the upper 4 bits as 1111, which will give 0, sorry, F 0000, 0, 0000, 0, 0000, 0, 0000, and the maximum address for RAM is 1111, which is F0111 is hexadecimal 7, 1111 hexadecimal H, F1111 hexadecimal F, 1111 hexadecimal F. So now the address space for RAM is F0000 to F7FFFH. Now the address space which we have selected for accessing any memory location of two 16K by 8 ROMs is F8000H to FFFFH, and the address space given for accessing any memory location of two 16K by 8 RAM blocks is F0000H to F7FFFH. One is from F000 to F7FFF. The next memory location is F8. So the consecutive memory locations are being assigned for RAM and ROMs. And the address FFFF0H is also assigned for ROM. Now we will see how to interface these two blocks. From this address space, we can see that A15 is used for differentiating whether it is ROM or RAM. Next, the memory blocks which are 4 in number, that is two 16K by 8 ROM blocks and two 16K by 8 RAM blocks. These 4 memory blocks arranged as shown in figure 1. On right hand side we have even address memory bank. On left hand side we have odd address memory bank. If A0 is equivalent to 0, that is the LSB bit of address line out of A0 to A19, the LSB bit we are taking either for address is odd address bank or even address bank. So if A0 is equivalent to 0, the address is for even, then the lower memory chip is selected, which is there on right hand side in the diagram, and for it is for 8-bit data transfer. Suppose if A0 is equivalent to 1, then it will select the odd address memory bank and 8-bit data transfer we can take, which we are shown in left hand side in the figure 1. The next control signal which we will take is BHE bar, which is bus high enable. Whenever bus high enable is equivalent to 0, it indicates the upper memory chips is selected, indicating the 8-bit transfer at odd address. For selection of the memory block, these two, compulsorily we have to maintain BHE bar is equivalent to 0. Next, what are the various data transactions we can have? Here it is. Either you are passing an address. If I am passing an address, this address may be access any memory location of RAM block 1 or block 2 or block 3 or block 4. In 8086 processor, the data transfer which we are going to be take is either it may be a 8-bit data transfer or 16-bit data transfer. If it is a 16-bit data transfer, we have to select the two memory chips, either it may be ROM or RAM. Suppose if the data which you are accessing with memory is 16-bit size and corresponding to ROM block, then we have to select both block 1 and block 2. And if the data size is 16-bit size corresponding to RAM, then we have to select the blocks B3 and B4 if it is a 16-bit data transfer. If it is a 8-bit data transfer and it is related to ROM, then we are going to be enable either block 1 or block 2. If the address corresponding to RAM block and the data size is 8-bit, then we can select either block 3 or block 4. The next objective is we have to design the decoding circuit that will indicate when we have to select block 1, when we have to select block 2, when we have to select block 3, when we have to select block 4. So in the figure, if you observe, the block 1 is selected for two cases. The first one is if it is 16-bit data transfer with respect to ROM, then we have to select both block 1 and block 2. If it is 8-bit data transfer and it is odd address, then we have to select B1 if it is ROM, and B2 will be selected if you are accessing the data from a even address bank and the size of the data is 8-bit corresponding to ROM block. And if the data transfer is 16-bit size corresponding to RAM, then we have to select both block 3 and block 4. If the data transfer is 8-bit size from the odd address bank, then we have to select block 3. For accessing any memory location from the even address memory block of RAM block, then we are going to be select B4 block. So now the decoder we are going to give with three signals. One is BHE bar and A0, A15. Whenever BHE bar is equivalent to 0, 0, whenever these two bits are 0, 0, it indicates it is a 16-bit data transfer. Whenever these bits are 0, 1, as BHE bar is equivalent to 1, it is lower 8 bits corresponding to even address, and the size of the data is 8-bit. Next, if A0 BHE bar is equivalent to 10, then the size of the data, it is 8-bit size. Taking from odd address, as BHE bar is equivalent to 0, it is upper 8 bits from odd address bank. 11 is not allowed because either you can have a 16-bit data transfer or 8-bit from upper or lower memory bank or even odd address bank. Similarly, here, if it is a ROM block, we are going to be write these two lines as 00, indicating it is 16-bit address. 01, it is 8-bit from even address. 10, it is 8-bit from odd address. For differentiating, either it is ROM or RAM, we have to select the A15 pin. If A15 is equivalent to 0, then it is corresponding to RAM. It is related to RAM. And if this bit is 1, it is corresponding to ROM. So the address mapping, we have selected A15 for differentiating, either accessing the data from RAM block or ROM block. If A15 is 0, the address is corresponding to RAM, and if A15 is equivalent to 1, the address is corresponding to ROM. Now, by combining the decoding, if A15 A0 BHE bar is selected as 000, then it will corresponding to a word transfer, that is 16-bit size from D0 to D15, and the banks which we are going to be selects are even and odd address of RAM block, that is block 3 and block 4. So we have to enable the chip select pins of block 3 and block 4. If you given the address on A15 A0 BHE bar as 001, then it is a byte transfer, that is D0 to D7, only from even address RAM, that is chip select 4, which is block 4. When our A15 A0 BHE bar R010, it is a byte transfer, that is D0 to D15 from odd address. Only odd address is accessed in RAM, that is enabling block 3, which is nothing but chip select 3. If A15 A0 BHE bar R100, it indicates it is a word transfer, that is from the lines D0 to D15, 16 bits of data corresponding to RAM. So we are going to be take a 16-bit data from both even and odd address of RAM, which is block 1, block 3, by enabling chip select 1 and chip select 2. The next possible combination for A15 A0 BHE bar is 101, which will signify it is a 8-bit data transfer, that is on the lines D0 to D7. Only even address in RAM is accessed by enabling the block 2 with enabling chip select 2. For lower 8 bits transferring, we had to give the pins A15 A0 BHE bar as 110, which will give the byte transfer on the lines D0 to D15 from the odd address. So only odd address in the RAM is accessed by enabling the block 1 with chip select 1. So this table will shows the selection of chips take place. For enabling either block 1 or block 2 or block 3 or block 4, we are going to take a decoder, which is 3 to 8 decoder. This decoder will functionate with the control signal A15, A0 and BHE bar. These lines are used for enabling any one of the output. Whenever we configure these bits as 000, then we have to configure for 000 combination, we have to enable both chip select 1 and chip select 2. 000 means it is RAM, so it is block 3 and block 4. For 001, which we are going to be enabled, or the data transfer is 8-bit size, the corresponding to even address. So we are going to be enable the chip select 3 even address. Next, for 010, which is odd address bank, we are going to enable chip select 3. Next, 100 combination. 1 indicates it is for ROM block, and these are corresponding to RAM blocks. Whenever these two bits are 00, it indicates it is 16-bit transfer. So we are going to enable the chip select 1 and chip select 2. For 101, which is a 8-bit data transfer, and the memory block which we are going to be enabled, here it is even address, which is nothing but chip select 2. For 110, for this combination, we are going to take a 8-bit data transfer from odd address, which is nothing but chip select 1. Now, if you observe these cases, the chip select 1, we have to enable whenever the combination of the decoder input is 1, 0, 0 and 1, 1, 0. If any one of these combination is there, then we have to enable chip select. So the R case we will take. The chip select 2, we are going to be enable this chip CS2 whenever it is 16-bit transfer, that is 1, 0, 0 combination or 1, 0, 1 combination. Similarly, the chip select 3 will be enabled for the combination 0, 0, 0 case, or whenever these lines are 0, 1, 0 for the decoder. The chip select 4, block 4 will be enabled whenever it is 16-bit data transfer with respect to RAM, that is enabling the chip select 3 for the decoder input case 000 and 001. So any one of these case, so we'll go for operation. So now for the decoder, the inputs are A15, A0, BHE bar. Whenever these 3 bits are 100, this output signal, I'll take this output signal as Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. If the inputs for decoder is 100, then the output which of the decoder which it is going to be enabled, here it is Y4. 110, Y6. Next 100, it is Y4, or 101, which is Y5. 000, Y0, 010, Y2, 000, Y0, 001, Y1. Now if you observe the chip select, we are going to be enabled whenever these lines are given with OR operation. For chip select 1, we are going to take a OR gate. The inputs are Y4 or Y6 for enabling the chip select. In the diagram, it is given as active low signal. For getting active low signals, we will put a inverter at this point. And the outputs of decoder, if you observe, these are also active low signals. So at the input side also we are going to get inputs are active low signal. The equivalent circuit for this is AND gate you can replace with OR gate. OR gate you can replace with AND gate, vice versa. If you have buffer, remove it. Here also if you have buffer, you can remove it. Then output side also you can remove it. So now this is you can done by using a AND gate here. Otherwise, you can go for directly connecting these lines with the corresponding logic. So now for enabling the chip select 1, we have to give the inputs for this AND gate is Y4 and Y6. For enabling the chip select 2, the inputs for AND gate we have to give is Y4 and Y5. For enabling the chip select 3, we are going to give the inputs are Y0 and Y2. For enabling the chip select 4, we are going to give the inputs are Y0 and Y1. So this is for enabling the corresponding chips based upon the address which you are passing. As the upper two blocks are RAM, we are going to have only the read signal corresponding to memory. So memory read signal is connected to output enable signal of the RAM blocks. Whereas for RAM, we have both read and write permissions. The control signals which we are getting from the microprocessor is memory read and memory write operations. Apart from that, we require the address space. A0, it is for differentiating whether it is even address bank or odd address bank. Out of 15 address lines, that is A0 to A14, out of these 15 lines, for selecting any one memory location, we require only 13 address lines. So out of these 14, which one we have to take is, we are going to take A14 to A1 for accessing any one memory location. A0, it is used for differentiating either it is odd address bank or even address bank. So the address space which we are going to be connect here, it is A14 to A1. Here also the address space which we are going to be connect is A14 to A1. Internally, how many address lines we require is 13 address lines. So from A0 to A13, they are going to be connect with A14 to A1. What about A0? A0, it is given as input for decoder. A15 also it is given for a decoder. So this is the entire interface diagram for 8086 processor to interface two 16K by 8 RAM blocks and two 16K by 8 RAM blocks with the suitable address mapping. Thank you all. The reference books are IARE and KM Burchandi, Advanced Microprocessor and Peripherals, Tata McGraw-Hill publication. Any edition you can prefer. I have referred the second edition which is published in 2006. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.